In our previous set of videos, we were looking to see if a hypothesis was equal to some claimed proportion, or if we could disprove that and prove it was different, less than, or greater than. In this set of videos, we're going to, instead of looking at how a proportion compares to a claim, we're going to look at two different groups and calculate the proportion from a sample from both groups and see if those two proportions are equal or different than each other. We're going to test two groups. This first set of examples is going to look at testing if proportions are equal. Let's say we have two medications that we want to compare for hives. Two medications for hives are tested. 20 out of 200 patients still had hives after 30 minutes on, we'll call it medicine A. 12 out of 200 patients still had hives after 30 minutes on medicine B. What we're really asking is there a difference at the alpha equals 0.01 level? Just as we did when a proportion was claimed to be equal to a number, we're going to go through the same 6 steps in order to test this hypothesis. Notice the difference here from the videos we saw earlier, though, where there was some claim about the proportion, the claim that the proportion equals a number. Here we've got two groups, two samples, and we just want to know, are the proportions different? So that's what leads us to testing for two proportions. So our first step is to identify the hypotheses. And the null hypothesis always has equality. So the proportion on medicine A is exactly the same as the proportion on medicine B. The alternate, what we're trying to prove is we want to know, is there a difference between them? So we're not trying to prove one is better than the other. We just want to know, is there a difference? And so that's going to be proportion A is not equal to proportion B. And you might recognize that not equal means when we draw our picture in the second step, we're going to have a two-tailed test. The hypothesized difference right in the middle is 0 because we're assuming they're exactly the same. No difference between them. But we have a two-tailed test. So in the left tail or the right tail, if one is bigger, if it is smaller, it doesn't matter. We just want to know, is there a difference in this two-tailed test? And so if we're really interested in the difference for these two-tailed tests, medicine A failed to work in 20 out of 200 patients. To find the difference, we would subtract the 12 out of 200 patients for medicine B, and we find out that difference is 0.04. Since that is positive, that 0.04 sticks us in the right tail of the picture, bigger than 0. And now that we know kind of picture-wise what we're looking for, let's calculate the test statistic. Just as we had a specific formula for testing if a proportion was equal to a number, when we don't know if two proportions are equal to each other, we're going to have different formulas for the standard error and the test statistic. The formula for the test statistic with two proportions is we take the proportion sample of the first group, subtract the proportion sample of the second group, and we divide by a standard error. Now, the standard error formula is different as well. The standard error formula is going to be the square root, it's this big long square root, of p sub c, which we're going to call the pooled proportion, times 1 minus p sub c, times 1 over the first sample size, plus 1 over the second sample size. But then wait a minute, what is the p sub c? Oh, we need to know that as well. P sub c, the pooled proportion, means if there weren't two groups, if the groups were lumped together in one group. So if we took all the successes from group A and added them to the successes from group B, and divided by the sample size from group A plus the sample size from group B, that would give us our pooled proportion. So we have to go through each of these steps in order to calculate the test statistic. So let's do that. First, we need the pooled proportion. For our pooled proportion, there were 20 successes in the first group plus 12 successes in the second group, divided by 200 patients in the first group plus 200 patients in the second group. When you put that in your calculator, you should get 0.08 for the pooled proportion. Now that we know the pooled proportion, we have to calculate the standard error. The standard error formula says we're going to take the square root of the pooled proportion, which is 0.08, times 1 minus the pooled proportion, 0.08, times 1 over the first sample size, which was 200, plus 1 over the second sample size, which was also 200. And so when I do that, we get 0.0271 for our standard error. We look like we're ready then to go to z, but with z, we need to know the proportion of A and the proportion of B. So there's actually two more things that we need to find. A lot of pieces to put together to get this test statistic. The proportion of group A. Group A, we had 20 out of 200 still have hives after 30 minutes. 20 out of 200 is 0.1. Group B's proportion, B was 12 out of 200. That's going to be 0.06. So lots of pieces to find for these two proportions. But now that we've got the pieces, we're ready to actually calculate that test statistic. Z, the test statistic, is the proportion of group A, which we just found out was 0.1, minus the proportion of B, which we just found out was 0.06, divided by the standard error, which is 0.0271. When I do that calculation in my calculator, I should get 1.48 for my test statistic. Now that we know the test statistic, we're ready to calculate the p-value. And I want to notice for my p-value, looking back at my picture, we said because the difference was positive, we're actually in the right tail. But if I do the norm.dist, it's going to give me the left side. We don't want the left side. So for my p-value in Excel, we have to do 1 minus the norm.s.dist command with the 1.48 and true, and that'll give me the right tail. The right tail, when I do that, is 0.0694. That is the right tail on my picture, 0.0694. But I remember this is a two-tailed test, so there's another 0.0694 on the other side, which means I need to multiply by 2 to get the true p-value of 0.1388. So moving to the top right, just so that everything's on one screen, we're ready for step E to make a decision on this hypothesis test. For our decision, we said alpha was 0.01 and our p-value was 0.1388. The p-value is bigger. And we know if the p-value is bigger, we do not have enough evidence to reject the null hypothesis. We're going to fail to reject the null hypothesis. So if I failed to reject the null hypothesis, when I get to my interpretation, we were not successful at rejecting. We will say there is not sufficient evidence comma, at the alpha equals 0.01 level to conclude. And again, we're going to go to the alternate hypothesis, putting the alternate hypothesis in context. the proportion of A is not equal to the proportion of B, to conclude that the proportion of people with hives after 30 minutes on medicine A and B is different. We don't have enough evidence to show that it's different. Again, notice we did not confirm the null hypothesis that they're the same. We just said we don't have enough evidence to prove they are different. Hypothesis testing always focuses on the alternative hypothesis and whether or not we proved the alternative.